Have you ever wondered what the universe is really made of, deep down? Everything you can see, everything you can touch, it's all built from tiny particles. And it turns out, every single one of those particles, and I mean every single one, belongs to one of just two teams. Today we're diving into those two teams, the fermions and the bosons.
But first, let's start with a question that sounds simple. Why aren't you falling through your chair right now? I mean, we all know atoms are mostly empty space, so what makes things solid? The answer has nothing to do with how hard atoms are. It's actually a direct consequence of the incredibly weird, invisible rules that these two types of particles have to follow.
Okay, let's get into it. At the most fundamental level, physics has this one giant sorting hat. Every particle is either a fermion, named after the physicist Enrico Fermi, or a boson, named after Satyendra Nath Bose. And this isn't just some convenient label, you know? It's a profound split that defines literally everything about how they behave and how they build our reality. Probably the easiest way to think about this is with a simple analogy. Fermions? They're the bricks of reality. They are the substance, the stuff that makes up all the matter we know and love. Things like electrons and the quarks that are inside protons and neutrons. Bosons, on the other hand, they're the mortar. They're the force carriers, the particles that communicate all the interactions, like photons carrying light or gluons holding the nucleus of an atom together.
So how do we sort them? What's the deciding factor? Well, the first clue is a purely quantum property called spin. Now hold on, don't picture a tiny little spinning ball. It's not like that at all. Spin is just a fundamental built-in property a particle has, just like its mass or its electric charge. And the key thing here is that it's quantized. It only comes in specific, pre-approved amounts.
And believe it or not, the sorting rule is ridiculously simple. It's how physicists first made sense of the whole particle zoo. If a particle has a spin that's a half integer, like 1/2, 3/2, and so on, boom, it's a fermion. If its spin is a whole integer, 0, 1, 2, it's a boson. Every single fundamental particle fits neatly into one of these two boxes, no exceptions. But here's where it gets really interesting. That spin value, it's just a symptom. It's the outward sign of something much, much deeper and weirder going on under the hood. The real difference between a fermion and a boson is hidden in what I like to call their secret quantum handshake. And it all comes down to their identity.
See, in our big everyday world, if I have two identical golf balls, I can still put a tiny mark on one and tell them apart. But in the quantum world, that's impossible. Two electrons are truly, fundamentally identical. You can't label them. They're completely indistinguishable. So if you were to swap their positions, the universe would have absolutely no way of knowing. This fact changes everything.
So to see just how big of a deal this is, let's run a little thought experiment. Imagine we have a system with two identical particles. The whole system is described by this mathematical thing called a wave function, which basically holds all the possible information about it. Now the question is, what happens to that wave function if we swap the two particles?
Well, it turns out the universe only allows for two possible answers. For bosons, if you swap them, the wave function stays exactly the same. We call this a symmetric wave function. But for fermions, this is the weird part. When you swap them, the wave function flips its mathematical sign. It becomes negative. We call this anti-symmetric. And this right here, this little flip, this is the real deep-down definition of what makes a fermion a fermion. So let's just lay it all out and see how it all connects. The half-integer spin of a fermion is directly linked to its antisocial, antisymmetric wave function, and that leads to this incredibly important rule called the Pauli Exclusion Principle. On the other side, the integer spin of a boson is linked to its social, symmetric wave function, which has no exclusion rule at all. This one tiny difference in their quantum handshake is what dictates their entire job in the universe.
So let's really dig into the consequences, starting with our fermions, the antisocial builders of the cosmos. That sign flip in their wave function isn't just some mathematical curiosity. No, it creates an absolute, unbreakable law of nature.
And that law is the famous Pauli Exclusion Principle. It basically says that no two identical fermions can ever be in the exact same quantum state at the exact same time. It's mathematically forbidden. If they tried, their combined wave function would have to be 0, which means they simply can't exist that way. They are fundamentally loners. They refuse to share the same quantum address. Period.
And the consequences of this one rule are, well, they're staggering. This is what creates reality as we know it. It's the reason you don't fall through your chair. The electrons in your body are fermions, and they're pushing back against the electrons in the chair because they just can't be in the same state. This principle forces electrons into different energy shells around an atom, which gives us the entire periodic table and all of chemistry. It's even powerful enough to hold up dead stars against the insane crush of gravity.
All right, now let's switch gears and talk about the other team, the bosons. Because their wave function is symmetric, it doesn't care if you swap them. They have zero exclusion principle. In fact, they do the complete opposite. They love to pile up in the exact same state altogether. They're the ultimate social particles, the gregarious connectors.
And this desire to share, to clump together, leads to some of the most spectacular and bizarre phenomena in all of physics. A force field, like a magnetic field, that's just a huge number of bosons all occupying the same space. A laser beam, that's nothing but trillions of photons all in the exact same quantum state, acting like one single giant wave. This behavior also creates mind-bending macroscopic effects, like superfluids that can flow without any friction at all, and superconductors that carry electricity with zero resistance.
So when you step back and look at the big picture, you see it. Our entire reality is built on this beautiful tension between two completely opposite behaviors. You can't have one without the other. They are truly the two pillars that hold up the entire cosmos.
It really boils down to something that simple. The standoffish, solitary fermions provide the stable, structured substance of the universe. They make things solid. They give things form. And the social, gregarious bosons, they provide the dynamic interaction. They're the messengers, the connectors, the energy that animates all of that fermionic matter. Bricks and mortar, substance and force. That's the whole shebang.
And this brings us right to the frontier of what we know. This clean, perfect divide between matter and force, fermion and boson, it's the bedrock of modern physics. But is it the final story? Big ideas like supersymmetry suggest that maybe there's a deeper connection, that every fermion has a secret boson partner and vice versa, which would unify them in a really profound way. And even weirder, in some 2D systems, physicists think they found evidence for anyons, particles that are, well, something in between. So this simple divide that builds our reality, it might just be the opening chapter to a much deeper, much stranger story.